Hi guys, it's Kate, and this is a walkthrough of one of the practice finals true-false sections. As you're going through this, try to pay attention to which problems are giving you the most trouble. Are you assuming things are true that are often false, in which case you're unable to think of counterexamples? Or are you thinking things are false that are actually true, in which case maybe you're fuzzy on particular properties or corollaries? Try to pay attention to which side you're falling on in terms of these habits, because either are addressed in different ways. Let's begin. Our first question states the tangent plane of the surface z equals f at a local maximum of f is parallel to the xy plane. There are a couple ways to reason about this. One is to think, okay, if I'm looking at a surface z equals f of xy at a local max, that means I'm at sort of a hill or a mountain in that function. And if I'm thinking of the tangent plane on the top of that hill, that is going to be a horizontal tangent plane. So this is true. Alternatively, you can also think, well, what if we thought of z equals f of xy as the level surface of some function of 3 variables, written like this. This is a level surface of a function of 3 variables, x, y, and z, where k equals 0. In order to find the tangent plane's equation, we find its normal vector by taking the gradient of this function. This is going to be -1 times the partial of f with respect to x, -1 times the partial of f with respect to y, and 1. But of course, we're at a local maximum of f. So the partial of f with respect to x at this point and the partial of f with respect to y at this point are both 0, meaning our normal vector at this particular point is going to be 0, 0, 1, pointing straight up in the z direction, which means that the tangent plane itself is going to be horizontal, or parallel to the xy plane. We move on to number 2. For any smooth functions, f of xy, x of t, and y of t, note that f is a function of x and y are both functions of t, we have that the derivative of f with respect to t is equal to the partial of f with respect to x times x prime of t plus the partial of f with respect to y times y prime of t. This is a true statement. It is just a restatement of the chain rule. This is the partial of f with respect to x, this is dx dt. This is the partial of f with respect to y, this is dy dt. At a local maximum of a function, f of xy, we always have f(xx) less than or equal to 0 and f(yy) less than or equal to 0. Is that true? In fact, it is. This is very similar to the second derivative test, except in multiple variables. Note that if f(xx) or f(yy), either of them, were greater than 0, then the function would be increasing in some direction. And since we're at a local maximum, that cannot be the case. In order to be at a local maximum, f(xx) and f(yy) must both be negative. Number 4. If 0, 0 is a critical point for a function f of xy, as well as for a function g of x and y, then the origin is a critical point of the function f plus g. Well, is this true? In order to be a critical point, the partials with respect to x and y must be equal to 0. The partial of f plus g with respect to x is the following. The partial of f plus g with respect to y is similar. We already know that each of these partials is equal to 0 because the origin is a critical point for both the function f and the function y. So this means that the sum of the partials will also be 0. So that means that the origin is also a critical point of the function f plus g. Number 5. The curves r of t as given and s of t as given intersect at a right angle at 0, 0. In order to determine the direction of these curves, we take their derivatives with respect to t. We see that regardless of your location on either of these curves, your direction vector will be the same, so it doesn't actually matter that we're at the origin. This is what the two direction vectors would be there. When we dot them together, we in fact find that the dot product is equal to 0, meaning that their directions at that point are perpendicular. Number 5, the quadric x minus y squared plus z squared equals 5 is a hyperbolic paraboloid. Now, perhaps you have reviewed your quadric surfaces and you know that one linear term and two squared terms will give you a hyperbolic paraboloid with a sign change on one of the squared terms. Or perhaps you have to go through and do the traces, in which case you see that one is going to be hyperbolas and two will be parabolas. In either case, those are two ways that you can arrive at the conclusion that yes, this quadric is in fact a hyperbolic paraboloid. Number 7. If u, v, and w are unit vectors, then the length of the vector projection of u cross v onto w is the same as the length of the vector projection of v cross w onto u. If we actually go about writing these out, we have two different expressions that look like this. Here, I'm using the equation for the scalar projection of one vector onto another, because that will give me the length of the vector projection. Note that what we're interested in as far as the lengths of these vector projections is the absolute value of either of these expressions. And u cross v dotted with w is going to be the same volume of the parallelepiped as v cross w dotted with u. The fact that one is divided by length w and one is divided by length u is not a problem, because here all of these vectors, u, v, and w, are unit vectors, so we're essentially dividing by 1. We know the numerators to be equal, and so both of these lengths are the same. Number 8 states that the partial differential equation, utt equals uxx, is called the Clairaut equation. This is false. It really just depends on whether you have memorized the various partial differential equations that we've used in this class. In fact, this is the wave equation. Number 9. The double integral of the square root of 1 minus x squared minus y squared over the region R equals 2 pi over 3, where R is the region that is the unit disk in the plane. We know that computing the double integral of some function, in this case the square root of 1 minus x squared minus y squared, gives the volume above the region R and underneath that particular function. Well, this function describes we'll call it northern hemisphere of the unit sphere, and so what we're looking for is 1/2 times the volume of the unit sphere. The volume of a sphere is 4/3 pi r cubed, which is going to be 4/3 pi. 1/2 of that will be 2/3 pi, or 2 pi over 3, so this statement is true. Number 10. There exists a vector field F in space such that curl is equal to 5x, negative 11y, 7z. A lot of people balk at a question like this and think, how am I supposed to reverse engineer a vector field that does this? In fact, you're not at all supposed to do that. Instead, we want to rely on one of the properties of vector fields, that the divergence of the curl of any vector field is 0. When we compute the divergence here, we get the following. 1, which is not 0, and so this vector field cannot be the curl for some vector field F. This statement is false. Let S be the upper hemisphere, x squared plus y squared plus z squared equals 1, and we're talking about the portion of it where z is greater than or equal to 0, with the normal pointing away from the center. Then the flux integral of the vector field 0, 0, 1 over this surface is 2 pi. Well, we know that divergence theorem involves flux integrals. That's a nice shortcut because we really don't want to go through the whole rigmarole of actually computing this surface integral. So let's take a look at the divergence theorem and what it says. Remember that the divergence theorem is applied when we have a boundary surface that bounds a solid. Now, of course, the upper hemisphere itself is not a boundary surface. It needs to be completed with the unit disk to become a boundary surface. So the S we're talking about is only this part. And if you add on the unit disk at the bottom, then it will become a boundary surface that encloses the entire solid, that is the solid upper half of the unit ball. Now what's interesting is that if we were looking to compute the divergence of this vector field over this solid half of a unit ball, note that the divergence of this vector field is 0. So we know that we would get 0 on this right-hand side. And so we know that the sum of the surface integrals of these two surfaces through the hemisphere that we care about and through the unit disk that we care less about it, but it does complete the surface, those two surface integrals are going to cancel each other out. They're going to give 0. And so what we know is that the surface integral through this hemisphere is equal to -1 times the surface integral through the disk. And this one is much, much easier to compute. In fact, when we seek to compute the surface integral of 0, 0, 1 over this disk, remember it's going to be -1 times the surface integral that we care about, the surface integral through the hemisphere. Well, what are we going to get? Well, the normal vector is going to be pointing downwards because we need an outward normal to apply the divergence theorem. And so the surface integral ends up being the double integral of 0, 0, 1 dotted with the normal vector, which on the bottom is 0, 0, -1. I'm running out of space here. But you understand that what ends up happening is that you're going to get -1 dA over that unit disk. And of course the unit disk's area is pi r squared. So the total flux through that bottom disk is -pi. We remind ourselves that the flux through the unit disk plus the flux through our hemisphere was supposed to give 0 by the divergence theorem. So that means that the flux through our hemisphere must be pi, which is not 2 pi. And so this statement for number 11 is false. Number 12. The points that satisfy theta equals pi over 4 and phi equals pi over 4 form a surface which is part of a cone. Well, if theta and phi are both held constant and the only thing that can change is rho, that means we only have one parameter. Surfaces have two parameters. Curves have one parameter, so what we're dealing with is a curve and not a surface. Number 12 is false. Number 13. The curvature of the curve r of t given here at t equals 0 is equal to the curvature of the curve s of t given here at t equals 0. Well, we take a close look at r of t and s of t, and we actually realize that everywhere we see a t in r of t, we just see a t cubed in s of t, which means we are parametrizing the same curve. Perhaps we're traveling it faster at different points depending on the value of our parameter, but that doesn't matter when it comes to curvature. Remember, curvature is talking about how curved a particular curve is, and since we're parametrizing the same curve, the curvature is going to be the same. Number 13 is true. Number 14. If f of xyz is a function and some vector field is the gradient vector field of f, then the divergence of that gradient vector field is equal to 0 everywhere. Is it true that the divergence of a gradient vector field is equal to 0 everywhere? Well, you can choose something to see. You can pick an actual function to try this out, and the answer is no. This is not necessarily true. What you actually get is the Laplacian. You get fxx plus fyy plus fzz. It is not necessarily equal to 0. So number 14 is false. Number 15. For any function f of xyz, we have the curl of the gradient of f is equal to the 0 vector. Well, this is going to be true. The curl of the gradient is equal to 0. That's because all the mixed partials are equal when you take del and cross it with the gradient of f. And by Clairaut's theorem, those mixed partials are equal, so every single component goes to 0. So already this curl of the gradient is 0. And then when you take the curl of a 0 vector, you're going to get a 0 vector again. So number 15 is true. For any vector field big F and any curve R parametrized on the interval from a to b, we have that the integral from a to b of big F composed of R dotted with R prime equals big F evaluated at the endpoint minus big F evaluated at the beginning point. This is false for a variety of reasons. One, it's trying to fool you about the fundamental theorem of line integrals, but remember that the fundamental theorem of line integrals involves the potential function, not the actual vector field. The other thing that could also cue you into the fact that it's false is that on this side, when we evaluate this integral, we get a scalar, we get an actual number out of it. But on this side, we have one vector over here minus another vector, which is a vector. So we have a scalar on the left-hand side of the equal sign and a vector on the right-hand side of the equal sign. Either way you look at it, this statement is false. It's trying to ring some bells about the fundamental theorem of line integrals, but it is not the fundamental theorem of line integrals. The fundamental theorem of line integrals involves the potential function, which we don't see anywhere here. There exist, this is number 17, there exist vector fields f and g in space such that the curl of f is equal to the gradient of g. This is false. You can only take the gradient of a scalar function. You cannot take the gradient of a vector field. The right-hand side of this equality doesn't make any sense. 17 is false. Number 18, if f is a smooth vector field in space and S is a closed, oriented surface, then the flux integral of the curl over the surface is 0. This is true. Couple ways to look at this. Note that if you have a closed oriented surface, you can apply the divergence theorem, which says that the flux integral of a vector field over a closed surface is equal to the triple integral of the divergence of that vector field through the solid that surface encloses. Now in our case, our actual vector field is the curl of another vector field, and so when we compute the right-hand side, we take the divergence of the curl of a vector field. That right-hand side is going to be the triple integral of 0 over a solid, which will always be 0. So 18 is going to be true. 19. The solid enclosed by the surface is z equals 2 minus square root of x squared plus y squared, and z equals square root of x squared plus y squared has the following volume, and it gives you a triple integral here. We remember that we find volume by using the triple integral of 1 over a particular surface. They're using cylindrical coordinates here. So the bounds in terms of z, the lower bound is absolutely going to be this square root of x squared plus y squared. The upper bound of z will be 2 minus square root of x squared plus y squared. Those have been correctly translated here. And then, of course, we want to think about, okay, where do these happen to intersect? You can rearrange and solve that equality to find that they intersect over a region known as the unit circle in the xy plane. And so our bounds will go from 0 to 1, theta bounds will go from 0 to 2 pi, and we do need a conversion factor of r there. And so this is the correct conversion of the triple integral 1 over the region, and it is, in fact, the volume for this particular solid. Number 19 is true. If r double prime is equal to 0, 0 sine t, and r of 0 equals 0, 1, 0, and r prime of 0 is 1, 0, 0, then r is equal to t, 1 plus t, t minus sine t. Yikes, that's crazy. Let's pick it apart piece by piece and see if it's consistent. Okay, well, if r of t is this, and we evaluate it at 0, sure enough, we do get 0, 1, 0. And note that r prime of 0 has to be 1, 0, 0. R prime would be 1 here. Here we'd have another 1 up, and that's where it differs. Note that r prime of t, according to this r of t, would be 1, 1, and then 1 minus cosine t. But the issue here is that 1 right there, because our r prime of 0 has to be 1, 0, 0. And if I took r prime in terms of t, it would be 1, 1, and already that 1, 1 just has totally destroyed r prime of 0. So this is going to be false. And that's it for the true-false on this practice exam. Enjoy studying. As always, if you have any questions, don't hesitate to email.